Okay, we'll begin then. Well, happy Monday. It's week 2. Hope you all had a good weekend, and we'll continue on. So we left off just kind of talking about some basics of Bayesian inference. And we said in Bayesian statistics, we have this unknown parameter. The unknown parameter itself is a random variable. And so therefore, any kind of inference that you do with it, you have a few choices. And one is you can plug in a single number, like the mean of your random variable or the median, the mode of your random variable, something like that. Or if you want to get the expected value, you can do that, but it requires taking the integral. Okay, and so today we're going to introduce Monte Carlo integration, which is kind of like this generalized kind of idea where we're able to calculate integrals without doing any kind of actual analytic integration here, right? So we ended with this kind of baseball example, and we said, the posterior distribution has this random distribution. It's a beta distribution with these shape parameters, and we said, okay, using that distribution for the unknown parameter theta, what can we answer about this question? And we estimated it by doing an integral to get the expected value, right? And we did it analytically, and it required us to do a whole bunch of kind of gamma functions and work through that. But then we also estimated using kind of Monte Carlo method, and we said, rather than trying to calculate this quantity, right? So we have one function is this probability 3 choose 2 theta squared 1 minus theta. Okay. So that's our g of x, and then and rather than multiplying it by the PDF of a beta distribution, we just said, let's just generate a million values from the beta distribution, and then we'll plug those in. And when you generate a million values from the beta distribution, naturally, some values will be more common than others, or I guess certain ranges of values will be more common than others, and so those ones are going to get effectively weighted a little bit more heavily when you take the average. You add them all up and you divide by how many you have. You're going to have kind of more values near the area where there's a high concentration. So values around 0.27 are going to show up more frequently. Values around 0.8 or 0.01 are going to show up a lot less frequently. And so you plug all million values in here. You calculate g of x on all of those things, and you take the mean. And we got this number, 0.1671577. And we said, that's really, really close to the actual value. Okay. And so we're going to just kind of take this same idea here, where we just kind of plugged in a whole bunch of numbers, added them up, and divided by how many we have. And we're going to just generalize. And we're going to say the expected value of this function h of x applied to the random variable x, where x takes on this, has the PDF f, can be found, okay, or is equivalent to taking the integral of h of x times f of x across all of the possible values of x, or across the domain of x, all right, and that can be found by taking a sample of values, okay, and you plug it into h. So the notation is a little bit wonky to read. This is the notation used in the textbook by Casella. So that's one of the textbooks referenced, I guess, in our syllabus. And so this is, I'm using the same notation, although, depending on another, if you pick up another textbook, the notation will be slightly different as well. Okay, but basically, we have e of x, basically an expected value. This part I don't think is mysterious, okay? The little f here indicates the PDF that defines our random variable big X. So the random variable big X is defined by this PDF f here, okay? And then we are applying this function h to the random variable, okay? So it's the expected value of the function h applied to the random variable x, whose distribution is defined by the PDF f. And that's found by taking, it's equivalent to the product of h of x and f of x, okay, across all of the possible values of x in the domain here. All right, so this symbol represents kind of integrating across all of the possible values of x, and we're going to say this quantity can be approximated using Monte Carlo, a Monte Carlo method, and this is what Monte Carlo integration is we're going to take a random sample of values, okay, and that's going to be what this xj is. So we're going to take n values on the order of 10,000 to a million or something like that, and then we're going to just take h, apply it to those random values of x, and then we just add them up and divide by n. Okay, and so that's just the mean of a sample of n values randomly drawn from the density f, and we're going to just apply the function h to it. So just a little bit more on notation. Okay, so x, random variable, as defined by the PDF f, okay, for all x values in the domain of x, okay, or this region x is the support of x, and the support of x is defined as you have some value, a positive value for f of x for all elements of x in that support, okay? And then for everything outside of that support, your probability, your PDF is going to be equal to 0. And then the requirement is that when you integrate across everything, everything integrates to 1, right? That's just kind of the definition of a PDF. All right, and so this is going to be the expected value of x for random variable with density function f. Okay, so this is just coming straight from our textbook. This is under the assumption that we are able to sample directly from the density function. So our computer has a lot of kind of built-in random generation functions. So we have things like R-uniform to generate random uniform numbers. We have R-normal to generate normal numbers, R-beta. Pretty much a lot of these kind of, quote, standard probability distributions. We have some kind of R function to generate random values from that PDF, okay? So what we'll do is we'll generate a bunch of these values, n of them, and we're going to assume that they're generated IID, defined by the PDF f. Then we're going to apply our function h. So we apply calculate h for all of those values of x that we generated, and then we estimate this expected value by just kind of taking the mean, right? Add them up, divide by how many you have. So simple enough, simple enough. So that process is simple. Let's talk a little bit about kind of, I guess, how it works. This is not a formal proof, but this is kind of, I guess, just appealing a little bit towards our intuition regarding, say, the law of large numbers. So we're going to say as the number of values that we draw approach infinity. So, we're getting, of course, a million is far short of infinity, but, it feels like a lot of numbers to us, okay? So as that n gets bigger and bigger, okay, we can expect that the random sample that we have, okay, x, through xn, to become more representative of the distribution as defined by f. So whatever our distribution f is, as we generate more and more values, we can expect that random sample to look more like the actual distribution. And so I guess a slightly more formal way of stating that is to say that the empirical CDF, the empirical cumulative distribution function, which is denoted by capital F with a little hat, capital F hat, based on the sample, converges almost surely to the actual cumulative distribution function. I don't know if you guys have learned about like modes of convergence, but there's different modes of convergence. There's like convergence and probability, and I don't know, so that we have almost sure convergence, and so this is one of those things. And so all we're saying is that basically, as you generate more and more, a larger and a larger n, the empirical CDF gets closer to the actual CDF. Okay, and so as a result, your Monte Carlo estimate, this h bar sub n, okay, is also going to converge towards the actual expected value of h of x. Okay, so what does it mean for the CDF to converge to the CDF, the empirical CDF to converge to the CDF? So the empirical CDF, the definition of that, okay, and I took this straight from Wikipedia, says that if we have a bunch of observations of x, okay, and they're all IID, and they're all coming from the same cumulative distribution function f, okay, the empirical CDF is just the number of elements in the sample that's less than some quantity t divided by n, okay? And you compare that to the actual definition of the CDF, which is what is the probability that x is less than or equal to t, okay? So, so you can kind of see how these two things are closely related. This one is giving you, what is the probability that your random variable x is less than some quantity t? And then here, if you have an actual sample, you're basically estimating this quantity by just kind of counting, what proportion of values in your sample are less than t, okay? So this, if you had to estimate this quantity using your sample, you'd just naturally use this thing, okay? And so the eCDF is just an empirical estimate of the CDF, where the probability of x being less than or equal to t is approximated using the observations in our sample. Okay, so okay, so I think I covered this last week as well, but again, in R we have a bunch of these different functions, and so you have, so for like the normal distribution, you have D norm, P norm, Q norm, and R norm, okay? D for density, and that's going to give you your PDF if it's a continuous, or a PMF if it's discrete. P is for cumulative probability, that's going to be the CDF. Q for quantile, and that's going to give you the inverse CDF. And then R is for random, okay? So a couple things, D norm, or actually the density, can be greater than 1, okay? Whereas the cumulative probability, its maximum value is 1, right? So the CDF has a range going from 0 to 1. You're never going to get a CDF greater than 1. But as far as the density goes, the density can be greater than 1, okay? The density is always non-negative, but it can definitely be greater than 1, okay? The quantile, technically, it's the input range is always going to be between 0 and 1, okay? The domain for which it's defined, but then the output could go from negative infinity to positive infinity, okay? And then random is going to just generate random values. So here, this is an example of an empirical CDF, and this would be a terrible one, but here I've generated 5 random values from the uniform distribution. Okay, 5 random values from the uniform distribution. My values are 0.201, 0.265, 0.37, 0.57, and 0.908. Okay, and therefore my empirical CDF looks kind of like this. So let me actually, little corner over here. So remember, it's the proportion of values less than or equal to, t, or I guess in our case, x here. So if I plug in x is 0.1, what proportion of values in my sample are less than 0.1? Right now is 0, okay? And when I get to 0.2, it's still 0. But then when I get to like 0.21, if I plug in 0.21, then one value in my sample is less than 0.21. And so my empirical CDF jumps up to 1 out of 5, 20%, okay? If I plug in, say, 0.3, okay? At 0.3, I have two values less than 0.3, so I'd get 2 out of 5, and so that jumps up to 0.4. And then if I plug in 0.4, then I have three values less than 0.4, so that jumps up to 0.6. And then, if as x gets bigger to 0.6, now I have four values less than that. And then at, say, 0.8, I still only have four values. And then at 0.95, now all five values are less than that. And so my empirical CDF is now 1. Okay, so this is what the empirical CDF looks like based on this random sample of 5 uniform values drawn from the uniform distribution. Okay, so this is a very poor approximation just because it's based only on 5. But as I draw, so the theoretic the theoretic CDF for uniform distribution should be basically a straight line going from 0, 0 to 1, 1. Okay, so it should look like this, and our things do not line up perfectly well with the red line. Okay, but as I get a larger sample, so here is 10 random values. Okay, this is what the distribution looks like. So again, I don't know what my first value is, but probably something around, looks like 0.07. All right, so at around 7%, I got one value that's less than 1 out of 10. And then it looks like my second value is right at 0.2. So at around 0.2, I've got two values less than that. And then it looks like our fourth value from the random uniform is a little bit less than, like 0.38 or something. So at 0.4, I have four values, and so on and so forth. And again, it's just randomly distributed, and so it doesn't line up perfectly, but it does a bit. This CDF looks a little bit better than this one. And as I get more and more, so here I've got 100 random values drawn from the uniform distribution. This does a slightly better job, okay? Again, not perfect, but a better job of approximating the theoretic. So the theoretic is in red, and then our empirical CDF, which is just what is the proportion of values in my sample that falls less than, say, 0.4, okay? That's where we are here. At 1,000, this is what it looks like. So getting, this is just to illustrate, I guess, the law of large numbers and how the CDF and the empirical CDF starts to converge closer and closer to the actual CDF, right? And so, in our 1,000 values, we happen to get, a little bit of difference here, where if I said, what proportion of values are less than, say, 0.5, okay? Out of 1,000 values, it looks like we've got, 515 or something, so a little bit more than 0.5, okay? And then over here, I don't know, at 0.9 something. So when I said, what proportion of values are less than 0.9, okay, maybe only 885 or something, okay? Something a little bit less than 0.9, okay? But, for a lot of places, when I said, hey, what proportion of values are less than 0.2, all right, we're getting almost perfect alignment. So out of 1,000 values, it looks like 200 out of 1,000 values are less than 0.2. And so my empirical CDF estimate would be 0.2, and the actual CDF is 0.2 as well. So we're getting pretty close alignment there, okay? And then so by the time, here I'm at 10 to the 4. So 10,000 values drawn from the random uniform, and we're getting, it's pretty close, right? So again, it's random, so it's not perfect, but this looks like a pretty good estimate of the red line, okay? Same kind of idea with the normal distribution. Here I just said generate 10 values between -3.5 and +3.5. Oh no, I didn't even say that. I just said, just give me 10 random values from the normal distribution. And then here I said, draw the CDF from -3.5 to +3.5. Okay, so the actual CDF looks like this red line. And so it looks like the first value I got when I generated 10 random values was, I didn't even get like a -1. I got like a -0.9 or something, okay? I got two values that were very, very similar to each other. So when I plugged in the ECDF, you know, at 10% of my values are less than this number, and then 20% of the numbers are less than that. So it looks like I got like a -0.91 and a -0.90, okay? Just kind of by random chance. And so therefore, my empirical CDF looks almost like a straight vertical line right here, okay? Because I just happen to get two random values that are almost identical to each other, okay? So, so this is kind of the shape here. As I draw more values with 100 values, this is kind of the shape. So out of 100 values, I had one value that was less than negative, looks like two values that were less than -2, okay? So here's -2. So out of 100 values, I have two values less than -2. And so that would correspond to an empirical CDF of around 2% for what is the cumulative distribution function for values less than -2. And then, you know, you compare that to the actual CDF. This actual CDF for being less than -2, I think, is close to around -0.025, right? 2.5%, because you get an 85% between 2 and -2, so you have around 2.5% below -2. And so, you know, that's kind of close. As I generate a few more random values, this is kind of what we get. I can say, you know, what proportion of values are less than +2? All right, around +2. This actually lines up kind of close just by coincidence. So it looks like, you know, 97 or 98 values are less than +2. And then it looks like I only have two values that are greater than +2. So, so this end actually lines up pretty closely. You know, we got a little bit of misalignment here. Here it is for 1,000 values, and now we get pretty close alignment between the red line and the black line, between the empirical CDF and the actual CDF. And then so with 10,000 values, now we're getting very close agreement between the empirical CDF and the actual theoretic CDF. Okay, all right, before I forget, let me give you your first view quiz answer, which is the letter C. C as in cat. C is your first view quiz answer, C. Okay. So all of these things to say, all right, that as n gets bigger, the empirical CDF, okay, the ECDF, which is capital F hat, okay, based on the sample, will get closer and closer to the actual cumulative distribution function, okay? All of these plots are not, these do not make a proof, all right? This is not the proof of the law of large numbers, but it's just to kind of illustrate, this is the concept that we're applying here, right? It's, when we do Monte Carlo methods, we're hoping that, or we're expecting our estimate to be like a decent estimate of the actual thing. And we're just saying, you know, the actual thing, it's tough to calculate because it involves probabilities and stuff. And so, you know, the way we're going to get around that is generating random numbers. When we generate random numbers, we're expecting the bigger sample we have it to kind of reflect the actual probability distribution, okay? So the hope is that they provide a little bit of intuition behind, you know, why we're just taking a large sample and how plugging it in is able to kind of approximate the function, you know, when we're applying to a random variable. So, so let's talk a little bit of about some of the properties here, okay? So one thing we can show is that it is an unbiased estimator, okay? So this, the estimate, h bar sub n, okay, is an unbiased estimator of this. And so the definition of h bar sub n is that we just kind of plug in all of our random values of x into h. We add them up and divide by how many we have. We just take the sample mean of h applied to x, all right? And so when we ask what is that, well, we just pull this out, and the expected value of a sum is going to be the sum of the expected values of that random variable. And so here I can pull out the sum and the 1 over n. And so now we're going to just get basically, we can ask what's the expected value of h of this. And then as shown earlier, the expected value of this whole thing, okay, is just h of x itself, because x, the random values of x drawn from the distribution is coming from the that distribution. So the expected value there is going to be the expected value of x there. So adding them up, dividing by n. So this is an unbiased estimator. So as you get in the long run, you can expect your Monte Carlo estimate to be centered around the true value. What about the variance of this thing? Okay. So if this is our Monte Carlo estimator, then this is our variance. Okay. So the variance of this is, what is the variance of this whole thing? Okay. And so we can kind of expand this out. We've got the variance of each of these individual terms, okay, because we've got n of these terms here, and so this will be kind of the sum of all of these variance terms. And then when you have a constant 1 over n or whatever it might be as applied to the random variable, then when you get the variance, that constant gets squared. Right, so this is going to be 1 over n squared, the variance for kind of our first instance of the random variable, and then 1 over n squared for variance of the second instance of our random variable, so on and so forth. How many of these things do we have? We've got n of these things. So I've got 1 over n squared, variance of all of these things, and because they all are IID and they all have the same variance, then we got n of these terms. We're just going to have 1 over n variance h of x. Right? And this kind of, I think, aligns with, I don't know, we're accustomed to kind of seeing the variance term for a sum, following this kind of 1 over n, or variance term for a mean following this kind of 1 over n business by now, I think. Okay, so that would be the variance of our estimator. Okay, and then if you don't know, so the variance of our estimator is 1 over n of the variance of h of x, okay? And so that kind of puts us in a little bit of a spot here, because it's often the case where we don't know the variance of h of x directly, okay? So we can also estimate the variance of h of x, okay, using some of our identities here, right? So the definition of the variance for a continuous variable can also be found this way, right? So we can just take the difference between y and the expected value of y, and then we'll square that and multiply that by f of y. And so if we let y equal h of x, then we can say, all right, the variance of our estimator, the variance of h bar sub n, is going to be 1 over n, the variance of h of x, and then we're going to say the variance of h of x is going to be defined by h of x minus the expected value of this times f of x. All right, and so now, using kind of our Monte Carlo estimator, we're going to just take this whole thing and just say we're going to call this thing g of x. So now I've got basically g of x times f of x dx right here. Okay, so we're just going to let this whole quantity be g of x, and we're going to estimate this, right? So this is kind of how we've been doing our Monte Carlo estimation, and we're going to say, okay, this quantity, the integral of g of x times f of x, okay, across all the possible values of x, can be found by just taking our Monte Carlo estimate of this quantity. So I'm going to just draw a bunch of random values of x, plug it into g, take the mean. Okay, so so all of this whole integral here is going to get replaced by this estimate here. So now the variance of this, which is 1 over n times all of this, is going to be 1 over n times this quantity, which is 1 over n there, right? And then what is g of x? G of x is, you plug in h of x, and you're going to subtract off this. Okay, so this is my Monte Carlo estimate of the variance of h bar sub n. Okay, so we're just kind of doing this thing where it's like, if you don't know one thing, just estimate it, right? So we're just continuing to so I don't know what h bar is, so I'm going to estimate it. I don't know what the variance is, so I'm just going to estimate it. And we're just kind of using all of these definitions of ourselves that we have, and we're just using that to estimate everything. Okay, that does bring in like a bunch of uncertainty and things like that, and so that's why we just say, hey, make sure you get a big sample, all right? And it's the loose answer, but it's kind of the answer that works. You just generate a whole bunch of values, and then you get your answer that way. All right, so this is what we have, okay? And then we said, okay, well, what is this thing, right? So my estimate of the variance is all of this, and then we have to plug in this, and then so we're going to plug in our Monte Carlo estimate of this expected value quantity, all right? No surprise at this point. And so we're going to say the variance of this, our estimate of the variance of the Monte Carlo estimator is going to be 1 over n squared. And then we're going to just basically take the difference between each of our sampled values, right? So we have the randomly sampled value. We plug that into h, right? We also have our sample mean. So we have all of our sampled values. We plug those into h, and we took the mean of all of them, and we're just going to take kind of the difference between each thing and the mean. We square that difference, we add them up, we divide by n squared. So it's kind of like almost like the sample variance of what you have after you've plugged in all of the random values you have. Okay. So yeah. Because h bar sub n is effectively the sample mean of h of x, this thing here, okay, we can use the central limit theorem to approximate its sampling distribution. So the central limit theorem states that if you've got something that's a sample mean, its sampling distribution can be approximated by a normal distribution, okay? And the properties of that normal distribution is that it's going to have mean mu and variance 1 over n s squared. Okay, the mean is going to be your expected value, s squared being your variance here. All right, so we can say our Monte Carlo estimate itself is a random variable coming from the normal distribution, where the mean is the true value, and the variance is the variance here. Okay, and so we have 1 over n, the variance of this. We're going to call this v sub n here. All right, which is what we have right here, okay? And so we'll just kind of plug that in, okay? And so with all of this in mind, we can kind of create little confidence interval bounds, okay, for our random variables of h. Okay, here, let me give you your second answer. Second view quiz answer is the letter B. Second view quiz answer is the letter B. So I wrote, let's not get lost with all the math because there's a bunch of stuff on these slides here, okay? The important things are this, right? One is that we're able to sample values of x from f, right? And right now we're just kind of relying on our computer to do this. We're just gonna say, okay, the computer's able to use our norm or our beta or our binom, whatever it is, to generate random values from whatever distribution we have, okay? And if we're able to do that, we're able to estimate the expected value of some function h, and all we have to do is we just plug in our random values of x into that function h, we add them up and we take the mean, okay? So h bar sub n is the sample mean of plugging in those random values into your function h, and that works because of the law of large numbers, right? And then the other part is that because it's effectively just a sample mean, it's going to follow the properties of the central limit theorem, right? So the central limit theorem kind of defines how sample means, or I guess in reality it's sums of random variables, but the mean is effectively a sum with a constant, is going to be normally distributed, okay? And so because of that, we can estimate the variance of the estimator using, this quantity v sub n, which is effectively the kind of like your sample variance there. So let's just try a few examples of how we can use all of this, okay? So one is we can use Monte Carlo integration to estimate the integral of any function, okay? Any function on some closed interval. So whatever it is, let's say this is the thing that we want to estimate, right? So we've got some function h of x, okay, integrating from a to b. And let's say this thing is hard for us to integrate directly, okay? Well, what we're going to do, okay, is we're going to just kind of set this up so that we can treat it like we're going to draw random values from some interval here, okay? So we're going to say the average value of this is 1 over b minus a, okay, from a to b of this whole thing, okay? And then if you think about what is this quantity 1 over b minus a is the same as the PDF of the uniform distribution on the interval from a to b, okay? So if you have right, so if you have a to b, and this has a height of 1 over b minus a, this is the PDF of a uniform distribution from a to b, okay? And so all we're going to do is we're going to just say, hey, you know what? This is in the same form of integrating of h of x times a PDF, okay? So remember the Monte Carlo estimator. Where did it go? Okay, so this is all we're saying. Okay, we got h of x times f of x, so some function times a PDF, right? Some function times a PDF. The integral of some function times a PDF can be found by just plugging in random values into your thing and taking the mean. So that's all we're doing, is we're going to just say, if I have 1 over b minus a times the integral of h of x, I can bring that in, and I've got the integral of h of x times 1 over b minus a. That's going to be function times a PDF, and we can estimate this using this, all right? So the end result is, if I want to get the actual integral itself, I just take my estimator and I'm going to multiply it by b minus a. So what this looks like is we're going to just generate random values from the uniform distribution from a to b. We're going to plug in those values into our function h, whatever it is, okay? And then this estimate, the expected value here, is going to be 1 over n times all of that, okay? And that's going to be my h bar. And then to get the actual value the estimated value of the integral itself, I'm going to multiply it by the constant b minus a. Because this thing is equivalent to the kind of the average value of the function. All right, so here's an example. So here's some function. It's cosine of 50x plus sine of 20x quantity squared. Okay, estimate the following integral. We're going to integrate from 0 to 1 of this function, and we can ask Wolfram alpha for the answer. No, you know what? So I said do the integral from 0 to 1 of cosine 50x sine 20x. And so this is Wolfram alpha's true answer. Is see, this would be a pain to do in real life. I don't know, there's all of these trig identities and things like that. All right, so the actual answer is 0.96520. Okay, and this is what the function looks like. Going from 0 to 1, we're getting the area in between there. Okay, 0.96520. So this is what the true answer is going to be. So what we're going to do, this is what we're going to do. Okay. Oh, so this is what the function looks like, and we want to integrate this. So what we're going to do is we're going to just generate, a whole bunch of random values between 0 and 1. Okay, so here I'm going to say 10 to the 5, like 100,000 random values from the random uniform from 0 to 1. Okay, that's going to be my x. Then I'm going to plug in h of x, h being my function here, cosine 50x plus sine 20x quantity squared. So I'm going to just plug in those values, and then I compute the mean, and then technically I have to multiply it by the width of the interval, but my width of the interval is 1 in this case because I integrated from 0 to 1. So so I'm just going to compute the mean, and then I multiply it by 1 minus 0, or I just multiply it by 1, and I get 0.966863, which is kind of close. It's not perfect. Okay, 0.9652, and my estimate's 0.9668. Okay. Let me just kind of show you a plot of just the first. What did I do? First 100,000 values here. So just to kind of show you how our estimate gets closer and closer to the actual thing. So my estimate of the variance can be taken by taking basically the difference. So here, just for the first kind of m values, so my variance gets smaller as I include more and more values in my estimate. Okay, so we're gonna I'm gonna just kind of keep the first m values, and then I'm gonna calculate just what is the mean of those m values. So that's found by doing h bar sub n here is the cumulative sum. So if I take like just the first kind of n values and I divide by n, so if I have kind of 10,000 values here, I'm going to get 10,000 values of this is basically the cumulative mean here. And this is going to be kind of my cumulative variance. So this is the variance for any kind of given m is going to be the difference between any of my values and the mean squared, and I'm going to divide by m squared. So this is kind of my running variance. We're going to look at this, my standard error, and I'm going to just kind of put in a 95% confidence band by going 1.96 standard errors in each direction. And what we can see is that the true value, according to Wolfram alpha, is 0.965 or something, so just a little bit under 1.0. And we could see, in the beginning, our estimates are a little bit off, but it starts to settle down as we get more and more values. Starts to settle down closer and closer to the actual value, and we could see our standard error estimates also shrink. Okay, our confidence bands get more and more narrow as we approach, or as our n gets larger and larger. And so this is it after just kind of 10,000 values. If we continued this on to say 100,000, everything gets even smaller. Okay, but again, your samples, your variance, shrinks at a rate of 1 over n. So you need to get bigger and bigger samples if you want even more and more precise estimates there. But yeah, that's kind of how Monte Carlo integration works. It's just a way for us to kind of estimate any kind of integral or any kind of function just by generating random values and then kind of plugging them in and then taking the average. Okay, we'll wrap things up here. Let me give you your last view quiz answer.